Hi everybody, welcome back to the Feynman technique. Today we are going to be evaluating this absolute monster of an integral. Um, let's just get started, shall we? Alright, what are we going to do first? Okay, we're going to do Feynman integration. Let's go ahead and create a function f of t that is basically, it's kind of similar to this integral right here, except we're just going to let it be x to the t. All right. So let's see, what can we do now? Let's evaluate f prime of t is going to be equal to the derivative with respect to t of f of t. And we can use the Leibniz rule for differentiation under the integral sign to take the derivative of f of t directly by taking the partial with respect to t of the integrand. So we just get natural log x. All right, that's looking somewhat closer to our original integral I now. All right, let's see. What happens if we plug in f prime at I? Well, f prime of I is equal to this. Well, what's x to the I? Well, x to the I, we can rewrite anything as e, any function of x as e to the natural log of that function of x, because the e and the natural log cancel out. And then using the properties of logarithms, we can bring that I right outside. And then using Euler's formula, we can see that this is cosine of natural log x plus I sine natural log x. So if we take the real part of all of these things, if we took the real part of this, we would just end up with this. So, we can just say that our original integral I is equal to the real part of our function f prime evaluated at I. Okay, so where do we go from here? We need to find an explicit form for this. Okay, let's see. This can actually be broken up like this. This is actually, we can see this graphically. If we graph this function, it is equivalent to x squared plus 1 times x plus 1. They're the same function. Okay? And then, so we can say this. We can say that 1 over this is equal to 1 over this. Well, we can use partial fraction decomposition on this. Let's see. We can add an x and subtract an x to make it look like this. And then we just have a 1 over x squared. Okay, let's see. And then we can add an x here. Well, you know what? I'm just going to skip right to the answer. This is going to be equal to 1 half. Sorry, I already did this in advance. 1 over x plus 1 plus 1 half times 1 over x squared plus 1. This is just partial fraction decomposition. Minus 1 half times x over x squared plus 1. All right, so this, and let me make this a little bit more consistent. Put a multiplication sign there. So this is equal to this. All right. I'm going to zoom out just a little bit so that you can see a little bit more of the work I'm doing here. All right. This will allow you to see a few more steps. Okay, what are we doing now? Well, let's rewrite our f of t. So our f of t, we're actually going to have three separate integrals. So our f of t is now going to be equal to the integral from 0 to infinity of, let's see, we're going to get 1/2, and then we'll have x to the t over x plus 1 dx, and then plus 1/2, the integral from 0 to infinity of, let's see, x to the t over x squared plus 1 dx, and then minus 1/2, the integral from 0 to infinity of x to the t plus 1 over x squared plus 1 dx. All right, it looks like that didn't reproduce our entire f of t. Let me make sure that these things are actually equivalent. But don't forget, we're working with complex numbers. So, let's see that. Yeah, that perfectly matches up with that. All right, so we're still good. We're working with complex numbers, so we're not going to worry about the fact that it didn't recover this right-hand side of the graph there. All right, so what are we going to do now? Let's think. Well, we have a formula. Let me open up a new tab in Desmos. We have this formula right here. I called it the universal integral, and it was this. So let's copy this over to our other graph and use this to rewrite our f of t, because every single one of these integrals right here is in this form. So, by the way, I will post a link in the description to my derivation of that formula. So let's rewrite our f of t. F of t is now going to be equal to 1/2 times this thing when, let's see, what's our b? Our b is 1. 1. And what's our a? Our a in this case is t. So that's just t. All right. And then we'll get plus 1/2 of this thing when our a is t, but our b in this case is 2. And then minus 1/2, again, the same thing. Now our a is t plus 1, so we end up with a t plus 2. Our b is 2 again. Perfect. All right. So let's delete this graph. Let's delete all this junk. So now we just have f of t being equal to this. Okay. All right. But we want f prime of t so we can plug in I and take its real part. All right. So what I'm going to do is, now we could all take the derivative of this thing with respect to t. So I'm going to use a derivative calculator to speed up the process a little bit. Taking derivatives is a very mechanical process. If you know the rules and you're careful and patient enough, you can get the correct answer, and this is what it is. So f prime of t, I'm going to label f prime of t as f1 of t is equal to this. All right, and just to make sure, I'm going to put a parentheses around here and put a ddt. All right, so yes, these things are in fact equivalent. Oh, no, they are not. What happened here? Oh, yeah. Yeah, they are. So I was looking at the wrong thing. Okay, yes, these are exactly the same thing. Okay. Sorry about that. Okay, I was like, derivative calculator never makes a mistake like that. I mean, it never makes, it might make a mistake on when you try to do integrals with it, but it never makes a derivative mistake. All right, so now, let's see. This is f prime of t, so now we use the fact that I is equal to the real part of this thing evaluated at I. So we're taking the real part of this thing evaluated at I. And for this part, I am going to use artificial intelligence to actually take this. All right. And let's see what it comes up with. I will be right back when it's done figuring this out. All right, guys, I am back, and I used ChatGPT's latest reasoning model to do this. It is O4 mini high, and this is what it says it is, and I'm going to plug it in right now, and let's see if it's actually right. So pi squared over 8 times, and it says cosine hyperbolic of pi over 2, sine hyperbolic of pi over 2, times 1 over sine hyperbolic pi over 2. I'm not sure why it didn't just say sine squared hyperbolic pi over 2, or sine hyperbolic squared pi over 2. So I'm just going to do it myself. Minus 4 times cosine hyperbolic of pi over sine hyperbolic squared of pi. That is it. That is, in fact, the answer to that integral. Wow, guys. All right. Artificial intelligence has come a long way. Now, you still can't just plug this in. It's not going to spit the answer to that integral out. You still need to work through it, but you can use the artificial intelligence to take the real part of some ridiculous complex numbers pretty quickly. All right, guys. But that's it. That is the answer. All right, guys. Hope you enjoyed that, and we will see you next time.